Good morning, afternoon, evening. How y'all doing today? Welcome back to Mr. Morrow's Honors Geometry class. Today we're going to continue with similarity and whatnots, and we're going to talk about congruences and proportions in similar triangles. I do need you to remember something though. Knowing that triangles are congruent, okay, allows us to use CPCTC, right? Congruent parts of congruent triangles are congruent. Well, guess what? Once you know or can prove that triangles are similar, then that allows you to activate the definitions of similar triangles, or polygons rather. And remember that similar polygons, congruent corresponding angles, and corresponding sides are proportional. So that allows you to activate this, okay? So we're going to start with some easy proofs just to show you what I mean, and then we'll get a little bit more difficult as we continue. So for example, number one, I tell you that triangle ABC is similar to triangle DEF. Oh, okay, sorry about that interrupting, guys. So triangle ABC is similar to triangle DEF. They want to prove that angle A is congruent to D. This is a no-brainer, guys, as long as you know the properties and definition of similar triangles. Given, ABC is similar to DEF. Awesome. Well, if they're similar, then we know that corresponding angles are congruent. And we know that A corresponds with D, not because of the figure, but because of the actual writing, the letters. So we can automatically say angle A is congruent to angle D. Corresponding angles of similar triangles are congruent. Yes, sir. Okay. Now, some of you may ask, can I say definition of similar triangles? I guess you can, but the true reality is that corresponding angles of similar triangles are congruent. Okay, number two. Again, they tell you that triangle ABC is similar to triangle DEF. Yes, sir. That's given. You can't use that with sides. Not that. You can't say it's congruent. But you can prove this right here. I can prove automatically, if I know that ABC is similar to DEF, doesn't AB correspond to DE? Guys, right? Not because I say so, but because AB corresponds to DE, right? And then doesn't AC correspond to DF? Not because I say so, but because it's written. Yes, sir. It's exactly like the CPCTC. Thank you, my brother. It's just definition of similar triangles. Yes, sir. No, you cannot use CAST. No. You can say either definition of similar polygons, or you can say corresponding sides of similar triangles are proportional. You can say either one of those two. So since AB to DE equals AC to DF, that means that the sides are proportional, and that's an absolute once you've already proven or have been given that the triangles are similar. It's not bad, right? But you got to know those two. I put these two up here on purpose because that's what should activate in your brain whenever you have a similar triangle. Similar triangles, congruent corresponding angles, and corresponding sides are proportional. Okay, next, number three. Let's get a little bit tougher now, but not too bad. Again, ABC is similar to DEF. Should be an A there, sorry. ABC is similar to triangle DEF. I want to prove that AB times DF equals AC times DE. Okay? Before this stresses you out, remember that when we have a proportion of sides, we can cross multiply them, remember? And the cross products will be equal. That's the means extremes product theorem. Some of you are looking at me like a deer in headlights, but we already learned this. So let's go over it. ABC is similar to DEF. That is given. If we are saying that we're trying to prove that AB times DF equals AC times DE, That should activate in you, hey, wait a second. We're cross-multiplying the proportional sides. So AB to DE, think about what I just did. AB to DE equals AC to DF. They have to. Why? Because corresponding sides of similar triangles are congruent, or are proportional. Now from there, if I take this proportion and I cross multiply, whoa, sorry about that, and I cross multiply, doesn't AB times DF equal DE times AC? And that is called, we'll just get rid of you here. And that is why? Because of the means extremes product theorem. Remember that once you have your proportional sides, which you have them right here, they're proportional because the cross products are congruent. And that is the means extremes products theorem. There's also the means extremes ratios theorem, which lets you rearrange those ratios any way you want as long as it's a true statement. Okay? Now we're going to get a little bit complicated. So hopefully you guys are seeing where I'm going with this. Okay, number 4. BD is parallel to CE. Okay, awesome. And I want to prove that AB times CE is equal to AC times BD. Now the first thing I should have done before, let's clone this. Let's bring it down. Okay, now let's work. Okay, first things first, given of course, BD is parallel to CE. Now we're going to have to go back in the recesses of our minds, and we're going to have to remember some stuff here, guys. From here, I can automatically say that angle ABC, which is this guy right here, is ABD. Yeah, you're right. Thank you, my brother. ABD is congruent to angle C, which is here. Why? Hint, hint. What letter did I just do? The F, right? So that's corresponding. Remember, guys? Corresponding angles are congruent if they're in between parallel lines. From here, I can now also say that ADB is congruent to angle E. Why? Corresponding angles are congruent. You with me here? Now I can say that ABD, which is this top little triangle here, is congruent to ACE right here. Why? AA, angle, angle. Very good. Excellent, gentlemen. Are you with me here? Okay. Think about what I'm trying to prove. I'm trying to prove that AB times CE equals AC and BD. So I'm working with AB and AC, and I'm working with CE and BD. So let's make that proportion. AB, which is this guy, to AC, which is this guy, is equal to BD to CE. Small to large, small to large. Are you guys seeing that? Promise? Okay. That would be corresponding sides of similar triangles are proportional. Or you could say definition of similar triangles. See a lot of you getting upset because you don't want to write that down. I get it. And then last but not least, we would have AB times CE, because when you cross multiply, will equal AC times BD. Why? Means extremes products theorem. Does that make sense? It's not too bad, right? Not too bad. Okay. Now, here, I know you guys are probably going to make fun of me, but I really like this because I made this cool little drawing and I was pretty happy with it. I'm not gonna lie. Pretty happy with it. Pretty excited. Pretty excited. Got a little telephone pole. Got a little flag pole. You know, go USA. Got a little picture of the sun. You know, it's pretty cool. Now, what I really like about this, I got the sun's rays. What? The reason why I did that is I want you to understand why these similarities occur. Okay, the sun's rays are almost parallel whenever they shine down on Earth. We're so far away from them, from the sun. I think it's 93 million miles. That since we're so far away, when the rays do hit Earth, they hit Earth in parallel formats, in parallel lines. So that's why we create similar triangles with shadows. While walking and enjoying the weather, John noticed a 20-meter flagpole cast a 25-meter shadow. I don't know what a shadow is, but shadow. Nearby was a telephone pole that cast a 35-meter shadow. How tall was the telephone pole? And then I explain again why we get similar triangles, because of the sun's rays. So they're going to be similar because of angle. The angle here will be congruent to this angle. And then when we're talking about a vertical object, this is a 90-degree angle. This will be a 90-degree angle. So they're similar because of angle. So not just because I say so or because the book says so, but because it's science. It's a proof. It's real. So we have a 20-meter flagpole, and it's cast a 25-meter shadow. And we have this, whoa, sorry, I'm talking about the flagpole. It's a cool little flagpole there. And then we've got the telephone pole that casts a 35-meter shadow, and it's X meters tall. Yes, sir, my brother. Yeah, brother, how do you do it, my man? No. Okay, listen to what he said, and let me show you why he did it wrong. He went 25 to 35 equals X to 20. No. You can't do it like that. Okay, you see how you went from small to large, but then large to small? Do you see what you did there? You could have done this. You could have done 25 to 35 equals 20 to X. That's fine. What I prefer, that's just me, you do it the way you want to do it. I like to just take the proportion of the large and set it equal to the proportion of the small. So height to shadow equals height to shadow. It really doesn't matter though, like I swear to you. Does not matter. Yes, sir. You could have also done 35 to 25, corresponding shadow to corresponding shadow, equals X to 20. Just remember, when you go from large to small on one side, you got to go large to small on the other. If you go small to large on one side, you got to go small to large on the other. That's why I like to just go height to shadow, height to shadow. So when I cross multiply this, I've got 25x equals 700, I believe. So divided by 25, so that's 28. So x equals 28 meters. And there it is. Does that make sense? Sir? Okay, that's a very good question. How do we know the telephone and the flagpole are perpendicular to the ground? I'm not being sarcastic at all. Usually, when you build a flagpole or a telephone pole, the engineers, when they lay the foundation, it's perpendicular. Now, could it have tilted a little bit over time? Sure. We're assuming that it's still perpendicular. It's a great question. Thank you, son. Yes, sir. Right, that's what I'm saying. It could not be perpendicular. We are assuming here that it is. Thank you, my brother. Yes, sir. And even if it's not, wait, hold on, sorry about that there, my brother. Even if it's not, when the sun hits this here, okay, it's definitely going to hit the ground at at some spot, correct? You with me here? This angle and this angle will be congruent for sure. So that means that this triangle here, these two triangles will be similar. So if that's similar, this will be proportional to that, creating similar triangles. Okay? Let's stop for the prayer. All right, guys. So a lot of questions have come up as far as how accurate this is. We are making assumptions. For those of you at home, just in case you're asking the same thing my boys are asking, yes, I guess this should be an approximation. But for all intents and purposes, we assume that it's perpendicular to the ground, and we assume that these are accurate, okay? Will they be off a little bit maybe in real life? Maybe, but for the most part, it's pretty darn accurate. But thank you for those questions. Great questions. All right, I think this is the last one. Yeah, last but not least. This is the monster, though. This is a heck of a proof here. But I like it. I like it. I think it works. It's good stuff. So let's just knock it out. All right. It is a long proof, though. It's 13. Okay. So let's see if we can keep up with this. Yeah, this is pretty tasty. All right. Number one, they are saying that you have parallelogram YSTW. So YSTW, the main figure here, is a parallelogram. Okay? And of course, that's given. Well, we know if it's a parallelogram, then angle Y has to equal angle T. And wait, before I continue, we're trying to prove that SX, okay, times YW is equal to SV times WT. So just to give you an idea of what we're trying to work with here. So it looks like we're going to have to prove some triangle similarities. So YT is congruent to, Y is congruent to T rather, because definition of parallelogram. I'm nice. I'll let you walk away with that. It should truly be opposite angles of a parallelogram are congruent, but I will let you slide with definition of parallelogram. Being that it's a parallelogram, we also know, or I'm sorry, not, this is a given. SX is given as perpendicular to YW. So SX is perpendicular to YW. Now think about it. If you can see, I've already got a little triangle here on the left side, triangle SXY. And I've got another little triangle on the right side, SVT. So I'm going to go ahead and say, let's be safe here, and say that SXY is a right angle. Why? Definition of perpendicular lines. Okay? You with me here so far? Then they also tell you that SV is perpendicular to WT. So remember what I told you. We have a little triangle over here being formed. So I think what's going to happen here is that angle SVT is also a right angle. Definition of perpendicular. So far it's a very long proof, but so far it's pretty simple. And if you're highlighting and using colors, like I've suggested before, you could already see two triangles that are similar here, can't you? Hopefully. You see that, first of all, that angle SXY is congruent to angle SVT because right angles are congruent. Now, from there, we know for sure that triangle SXY is similar to triangle SVT because of angle. You feel me there? Okay, now we're going to have to get some proportions going And we're going to still have to use some properties of the parallelogram. Hopefully you can see that Sx, okay, is proportional, Sx to Sv is proportional to Sy to St. Okay? You feel me there?
Yeah.
Why? Because corresponding sides of similar triangles are proportional. If I cross multiply those, I will get that Sx times St is equal to Sv times Sy, means extremes product theorem. And now here's where I blow you away. St is congruent to Yw. St, which is this guy, is congruent to Yw. Why? Opposite sides of a parallelogram are congruent. I will let you slide with definition of parallelogram. But if St is congruent to Yw, can't I go ahead and substitute here? I'm sorry. And Sy is also congruent to Wt. So Sy, I know we're almost done, is congruent to Wt because of the definition of parallelogram. Can't I now say that Sx is congruent to Yw because St got replaced with Yw, and Sv times Wt, they're both equal now. Why? Sy got replaced with Wt. Substitution property. I know you want to get out of here. It's Friday. Go study, watch the video. God bless you. Have a great day. Hope you learned a lot. Bye-bye, guys.